Hello friends, I'm going to derive the force for buoyancy in a video that you'll watch, and you'll practice using it in class tomorrow. If you have questions, please write them down, email me right away, or bring them to class. But I'd love to dive right in. Tomorrow you're going to be working in groups, as much on your own away from screens as possible if you're in a classroom. So this will hopefully give you what you need, but if you have questions, email me or bring them to class. Easy done. So this is how we derive buoyancy. This is true for any shape, which is kind of hard to believe at first, but I'm going to draw a box. That's supposed to be flat on the bottom. The pressure forces point perpendicular to the surface. On the bottom, they point up, which makes sense because if you have the weight of everything pushing down, these molecules experience a force above it pushing down, so they respond with a force up. What rule is that? This magic law of the universe. It's Newton's third law. So this couch supporting right now is pushing back up on me with an upward force. So it's actually pushing up in response to the weight of all the fluid pushing down. The ones on the side, I'm going to draw them accurately, taper down to be less because they're less deep. And the ones on the top are even less deep, so they are less. That is kind of the aha moment that I'm jumping to. So these are the pressure forces. Pressure, of course, being rho of the fluid depth G. The top is at depth 1, the bottom is at depth 2. Say it has some area A, and of course that means this is some height H. The pressure forces on the top we'll call F1. The pressure forces on the bottom we'll call F2. Yes, there are a bunch of individual forces, but let's add them all up and say they just sum to some net force F2, and here they sum to some net force F1. Pause. Which is bigger, F1 or F2? So this is some cross-sectional area A. Sorry, A isn't this whole area. A is the area of the top and the area of the bottom. Sorry. Let me maybe draw that in blue to not confuse that with any other area arrows. A is the area, the cross-sectional area that you can't see because this is a three-dimensional box. So A is kind of like this area here. This is a box, kind of like that. Right? Does that make sense? And so this area A here, this is also area A here. Area A times H, of course, gives us the volume of this object. That's area A, that's area A. So we have a force distributed over an area. We have force distributed over an area. Pressure. So which is bigger, F1, F2? Same area. Less depth means less pressure, which means less force. That's really important. Less depth. I'm going to write it like this, and not in complete sentences, but like less depth implies less pressure, which implies less force because it's the same area. So F1 is less than F2. The ones on the side cancel because they're equal, because they're the same depth here and here, left and right. F left pushing left, or F on the left side, however you want to say it. I'll say F pushing left equals F equals force, F pushing right. So they cancel. In terms of magnitude, I'll be accurate. The magnitude of them equal, so they cancel, which means we have a net force upward on the box. If I were to redraw the box, I have a net force upwards. We call call buoyancy, which is the difference between the pressure forces on the bottom and the top. Pause, breathe. This is air. You're actually experiencing buoyancy from the air right now, believe it or not. And I'd say, hey, I'm not floating. Well, no, because you're heavier than that buoyancy force, but it's more than 0. We'll calculate it in class tomorrow. You will. It is the difference between the air molecules pushing up on you. There's still a little bit of air underneath you, pushing up on you. It's all squeezing you, pushing you up. So buoyancy force always pushes up. So FB equals F2 minus F1. Point number 1, it's always up. Why? Remember, it's because this is always bigger than this, and this is the bottom, and the bottom is always deeper than the top. The bottom of an object is always deeper than the top. That's trippy. It's always deeper. It's always up, and it's always there. If you're in a fluid, you're going to have a buoyancy force. It might be really tiny, and so it's like negligible. It's like saying it's there, but it's not there. But it is always there, even if it's really tiny. So let's calculate it, and then we're done. So force, so pressure is force over area. So if I multiply by A, force is pressure times area. P2 times that area minus P1 times that area. P2 meaning the pressure at the bottom. P1 meaning the pressure at the top. Meaning we have density of the fluid, d2GA minus density of the fluid, d1GA. Notice I have density, G and A is the same, so I can factor those out algebraically, and I'm left with this, d2 minus d1. And if we redraw our object, sorry for the coarse drawing, this is d1, this is d2. The difference between them, this is the aha moment, is the height. What's area times height, everybody? Volume. This is volume, so this is density of fluid times the volume of the object times G. Now we want to be careful. I'm going to write the actual answer here. We were assuming the fluid was completely submerged. If it's, actually, I'll just erase the DIS. I'll explain what I mean by that in a second. So this is it, but I want to be careful. So if the fluid, if an object is partially submerged in a fluid, for instance, water, by any fluid, then there is no pressure on the top caused by that fluid. Now there's a pressure caused by the air still, but the buoyancy caused by this fluid will essentially mean that the D1 is 0. The water isn't acting on this part of the object, so it's irrelevant to the buoyancy. It's not irrelevant to the weight of the object. It's not irrelevant to what happens to the object, but it is irrelevant to the buoyancy. So this volume is irrelevant to buoyancy of the water, caused by the water. FB caused by the water, if this is water. They will experience a separate buoyancy caused by air, but in terms of, if we want to know the buoyancy caused by here, all that matters is we say, okay, now D2 is that, D1 is that, and so this is now not the height of the object, but a different distance, and this is no longer the volume of the object, but the volume underwater, or the volume displaced. Sometimes we say the volume submerged. So I'll write VDIS, and that actually is, I prefer that over time. If you like submerged, please, that's fine, but it is the submerged or displaced volume. I'm going to use those interchangeably. submerged or displaced volume is what matters. So our formula for buoyancy force is the density of the fluid, not the density of the object. You might say, but doesn't the density of the object determine whether it sinks or floats? Of course it does. We're not there yet. The buoyancy force is not the only force acting on this object. What keeps you to the earth? It's not buoyancy, it's gravity. Your density affects how heavy you are. Right? Okay, right? So that's a separate force. That's step 2. This is step 1. Step 1 is saying the density of the fluid times the submerged or displaced volume times g, what planet you're on affects it, of course, is the buoyancy force, and it's the sum of all pressure forces. So instead of drawing all the pressure forces individually and just saying, well, I have a trillion forces or infinite forces to add, well, you add them all up, you get a single force, and it's always up. Right? And this is the formula for it. Now, I will tease us, we will do this eventually, but if I have an object and it's under water or in a fluid, if it's air or water, doesn't matter, it will always experience a buoyancy force up. So if you have something that's in a fluid, just draw buoyancy force up, just like you would naturally draw mg down. This is going to be our diagrams. Now, if we have a different force, like drag or something, I don't know if I'm going to do that. It might. Life does that. We might add that, but regardless, this will always be there. And this will always be there. It will always look at least like this. Buoyancy force will always point up, mg will always point down. Now what happens? You say, does it go up? Does it go down? Well, is mg greater, is buoyancy force, sorry, greater than mg? Then it goes up, then it rises to the top. Is buoyancy force less than mg, meaning is it heavier? Is gravity bigger? Then it will sink to the bottom. This is what we'll practice in class. I don't think we're going to get here necessarily. We are actually. We must go right into this tomorrow. I just realized we'll do some simple calculations to see what will happen. To see what will happen. So much happening in terms of objects sinking or rising in a fluid. That's it. You guys are amazing.